Good morning. This is the ABET presentation of Electrical Networks of Analysis 2. My name is David Rodas, and our topic is about three-phase short circuits in power systems. The objective of the presentations are, first, establish the different types of faults that are in transmission lines at the transition stage. Second, analysis of the consequence of three-phase short circuits current fault in the transition stage. Third, we're gonna define the parameters for the choice of protective equipment in transmission and generation systems. But first, what is a short circuit? This generally occurs, it is accidental or intentional between two or more conductors, forcing potential differences between these parts to be close to zero. Now, these type of circuits have consequence. The first consequence, and that is one of the principal consequences, is the deterioration of the conductors. Second is the temporary or permanent damage to equipment. And third, it is the decreased efficiency in the rest of the electrical network. What is about the fault or short circuit current? This occurs when the impedance that it is opposed to the short circuit current establishment, it is highly inductive. So the current that is derivated from the neutral capacities tends to zero. Specifically in the transient circuits, for example, the resistive and inductive series circuits, the solution for the differential equation to determine the current fault, it is shown in this part. As you see, the current is equal to the maximum voltage divided by the impedance. That is multiplied by two parts. The main part, that is a sinusoidal wave, is called the AC component. And the second part, that is a sinusoidal wave multiplied by an exponential wave, it is called the DC component. These two terms, my next partner is gonna explain about these two terms. Thank you.
As highlighted at the previous point, the short circuit current has two types of DC and AC components. But before going into detail of this characteristic, it's worth highlighting two behaviors present by the proposed electricity grid. The first is stable behavior, which is obtained when all electrical variables, current or voltage, exhibit a constant sinusoidal behavior over time. Conversely, the second state, called transient, is the one where electrical variables tend to vary over time and sign behavior is altered, until it reaches a stabilization point of the aforementioned state. Retalking, the DC component is that component present only in the transient state, which allows to determine the magnitude of the resulting current at the instant of the abrupt change until it managed to stabilize. So this component presents an exponential decreasing behavior. The same can be a higher value than the current peak for the stable equivalent system. The AC component, also called a periodic component, is the sinusoidal component and is maintained to the stabilized state. It is the component that suffers displacement because of the DC component. Then the current graph versus the time is, if we remember the equivalent circuit proposed for this analysis, it presents an inductive passive component, which the course that was studied in this course prevent the abrupt change of current as seen. On the other hand, the voltage signal does not exhibit the same behavior, which generates a magnification of the current in a short period of time. Finally, to an importance of the study of this fault current is the design of protection, since they must be elaborate in order to withstand the abrupt change of current. present in the network and protect the system. Therefore, among the parameters to be considered, the effective value of current and the magnitude of that should be able to disconnect currently stand out.